Hello, welcome to lecture number 8, where we're talking about derivatives. Let's get right into it. Well, actually, let's not get right into it. I have this first slide here, which is supposed to be a reminder. You probably have seen at least a few of these concepts in pre-calculus, and we're going to be talking about them later. They are related to derivatives, so let's just remind ourselves what these terms here mean. If you have a function f, a secant line to the graph is just a line that intersects it in at least 2 points. I'm going to have a few examples down here. But then the tangent line, that's the one that's more important for us today. The tangent at a point, if you have a point on the graph, it looks like this. It's some x coordinate a, and then the y coordinate is supposed to be f of a. So if you're talking about 1 point, the tangent line is the line that indicates the direction along which the graph is going in the vicinity of that point. This is a very informal definition right here. And by the way, this line may or may not be well defined at that point. There are cases in which it simply does not exist. The other line that we'll sometimes talk about is called the normal line. It's just a perpendicular line to the tangent line at that point. So here are the examples here. I have a graph in red. The very first line here in blue, this one, you can call this a secant line because it intersects the graph in 2 points. The point with x coordinate -5 and the point with x coordinate -2. There are many secant lines to a graph. But the other blue line here is the one that's more important for us, tangent line. The tangent line at the point with x coordinate 1. You can see here that it's kind of grazing the graph right at that point. It's intersecting the graph in only 1 point, at least around here. If you really think about this line after extending it further, it is going to intersect the graph in another point later, but that's irrelevant. What's more important is that it's kind of resting on the graph, following the same direction that it does around that point. That's what a tangent line is. And in orange here, this is the normal line at that point. It's just perpendicular to the tangent. So as you can imagine, this remark here, tangent lines are not well defined at points where the graph has a sharp corner, which is called a cusp, or also at points where the function itself is undefined. So look here, for example, there are 2 places with x coordinates -2 and +2 where this graph has a cusp. So if you try to define a tangent line at those places, it's impossible to say, is it, for example, this line, or maybe a little bit more horizontal, maybe a little bit more like this. Every one of these could reasonably be called tangent at that point. So we just say it's simply not defined. Similarly for this other cusp. And also look at the point x equals 3. There is no value for the function there, even though you can probably guess what the graph would be doing around that point. If it were continuous, it would simply be extended on that point. But in cases like this, we also say there is no tangent line at that point. Okay, so we're gonna come back to this geometric meaning of tangent lines and the relationship between this and derivatives in the end of today's lecture. For now, let's just talk about derivatives. And I am of the opinion that it's probably best to do it this way. I'm simply gonna define it without any motivation. We're gonna work through a few examples and we'll talk about the motivations behind the derivative after doing this. One of them being the tangent lines. So that's the plan for today. Let's just consider this definition as something that we need to know. This is very important. So we'll jump right into it. If you have a function f and a point a in the domain of the function, the derivative of f at a, which is denoted f prime of a, is by definition, is defined to be the following limit if it exists and if it's a real number. This limit right here. You're going to take a limit variable age going to 0, and you're going to form this particular expression, which is called a difference quotient. We've seen this in many occasions before today. So in the numerator, you're taking f of a plus age minus f of a, and then dividing the whole thing by age. This is always a limit that's in the indeterminate form. If you think about this, what happens when you plug in h equals 0, at the top you're going to have f of a minus f of a, which is 0. At the bottom you also have a 0. So this is always a 0 over 0. It's always a limit for which you need to work. You need to simplify it somehow if you want to compute it. That's the definition of a derivative at the number a, whatever this a is. But by the way, if you do a change of variable in this limit, let's define a new variable y, which is a plus h, then the limit can also be written in another form. Both forms are correct. Both forms are useful in different cases, so you should know both of them. It becomes this. Just think about it. If h is going to 0, then this new variable y is going to a plus 0, which is just a. That's how I know that y is going to a. And you do similar tricks right here. Instead of a plus h, I'm writing y, because that's what y is. Instead of h in the denominator, I'm writing y minus a, because that's equal to h according to the change of variable. So you can work this out. This is what the limit becomes. And you can use either one to talk about a derivative. And here's the last line. In this case, in case this limit does exist and is equal to a number, we call the function f differentiable at a. You should know these two words, the derivative and differentiable. So here's an example. It's saying use both of the limits to compute f prime of 2 for the function x squared plus 4x plus 5. I copied down the two limits right here so we can see them. And this is a very simple example. We can try to find f prime of 2 by doing the definitions. Let's use the first one, for example. Limit as h goes to 0. So in the numerator here, we need to compute f at the number a plus h. Well, a is 2 in this case. The place where you are finding the derivative, f prime of 2. So we need to plug in 2 plus h into the function, then subtract f of 2, the whole thing divided by h. Let's compute this. Well, f is x squared plus 4x plus 5. So if you're evaluating it at the number 2 plus h, this is f of 2 plus h. Now I'm going to subtract f of 2. The whole thing divided by h. What does this become? Well, there's a lot of simplification to be done here. 2 plus h squared. 4 plus 4h plus h squared by the binomial theorem. 4 times 2 plus h is 8 plus 4h, distributing the 4, plus 5, and then minus whatever this number is, 4 plus 8 minus 5. So 12 plus 5, sorry, 12 plus 5 is 17. All right, now I'm going to group together the similar terms. There is just one h squared. Then there are two instances of 4h. And what do the numbers give you? 4 plus 8 is 12, plus 5, 17, minus 17. So there are no numbers left, which we could probably have guessed. Remember, I told you this limit will always be of the form 0 over 0. If you had a number here, you know something is wrong. All right, so what do we do with this limit? If you factor in h from the numerator and then simplify it with the denominator, that's how you do the simplification that's required. And then now this is a limit where you can plug in h equals 0 and get the number 8. That's your f prime of 2 for this function. Now this calculation was done using this first limit, the one with the h. The problem was asking us to use both. So now I'm going to use the second one, and we better find also the answer 8. So let's see. We are now trying to use this form where y goes to a. A is 2, remember? It's f of y minus f of a. divided by y minus 8. And now replacing f with what it actually is, f of y is y squared plus 4y plus 3, I believe. Just checking. No, plus 5 in the end. Sorry. All right, that's f of y. What is f of 2? We computed this above. It was 17. 2 squared is 4, plus 8 is 12, plus 5, 17. Divided by y minus 2. So this gives you, after simplifying this numerator, y squared plus 4y minus 12 divided by y minus 2. Well, plugging in y equals 2 is going to give you a 0 over 0, as it should. So we know that we need to simplify it something from here. And what is the way to simplify this? You want to factor the numerator, and you will most likely find a factor of y minus 2 in it. So if you try to factor the numerator, you're looking for two numbers with a sum of 4, product of minus 12. They are 6 and minus 2. This checks out, and now you can see the y minus 2 goes away. Limit of y plus 6 as y goes to 2 is 2 plus 6, which is 8, the same answer that we found above. All right, so this is how you compute a derivative at a point, the point 2, using the definitions. Now here's a remark. Basically, this remark is telling us, instead of having a point like the point 2, we can have a general point, a variable x. So the derivative f prime can be regarded as a function. What it means is that at every point x, where the function is differentiable, it just returns the value f prime of x. So look at this example here. Consider the square root function with the domain of 0 to infinity, with 0 included. That's the domain of the square root. They're saying, I'll find the derivative function f prime and its domain. In other words, they're telling us to compute f prime of x, where x is just a variable. We don't know what it is. It's different from the previous problem in that we don't have a number 2 in here. We just have a random x. But the calculation is the same. And in fact, you get to choose which one of the two limits you want to work with. Let's say, for example, the second one. Let's try to find f prime of x first. The domain, I'm using the second one here now. The domain of the function f prime will be the axis for which this calculation makes sense, for which the answer is well defined. So I'm using the second definition of limit, which means y goes to x, which is the number where the derivative is being found. And you do f of y minus f of x divided by y minus x. So let's do this. Y is going to x. The function is root y minus root x over y minus x. Well, this is one of those limits that require rationalization, you probably guessed. We're going to multiply and divide by root y plus root x. You should be good at doing this by now. You should have done lots of examples, so you should know how this works. For example, you probably know by this point that there is really no use in distributing out the multiplication in the denominators right here. The useful part about the rationalization was the numerators that gave us a y minus x. And now we can cancel that with the y minus x downstairs. This is going to leave us with just 1 over root y plus root x, which is now a limit for which we can plug in the value y equals x, giving us 1 over root x plus root x, also known as 1 over 2 root x. That's the answer that we find for the derivative. If you've taken calc before, if you know derivative rules, you probably even remember how to differentiate the square root. This should be the answer that you remember. So this is the definition of the function. F prime of x is always equal to this at any point x. We just need to give the domain of this. The domain is actually, think about for which x's does this computation make sense, in particular the final expression. You have a square root, so x has to be larger than or equal to 0. But actually it cannot be 0 because it's in the denominator this time. So you need x larger than 0 for this domain, which in interval notation would be like this, open at 0. So even though the original function was defined at 0, the derivative is not defined at 0. So now let's find some derivatives of more functions so we can get used to this calculation. The first function given to us is the constant function, f of x equals c. C in this problem will be just a parameter. Think of it as a fixed number. It could have been the number 3, for example. How do we find the derivative of this function? Let's use the age limit now. You're going to be using whatever limit you feel more comfortable with. The calculation in each one should be the same, the amount of calculation. So if h is going to 0, then the limit is like this. Remember, it's a plus h minus f of a. Sorry, f of a plus h minus f of a divided by h, where instead of a here, the place where we are finding the derivative is called x. That's just what you decide to call your variables. But anyway, the function f in this item is just a constant. It's c. So both f of x plus h and f of x are equal to c. And then c minus c is equal to 0. This is not actually a limit of indeterminate form 0 over 0. The function inside of the limit is the 0 function. Like before computing the limit, before trying to find the limit of numerator and denominator, we're actually going to say the numerator is a 0 in this problem. And 0 over h is always 0. So the function of which you're taking a limit is the 0 function, and then that limit is equal to 0. All right? Maybe one more step before I do that is this. Before we are taking the limit, we are simplifying the function down, and it became the constant function 0. That's why this limit is 0. So the derivative of a constant function is 0. Next item was a linear function, cx plus d. If you know calc already, you probably remembered the derivative should be the c number. So let me copy down the function here, cx plus d. What is f prime in this case? At a number x. Maybe I'm going to use the y limit this time. So y goes to x. It works like this. F of y minus f of x divided by y minus x. Well, f of y is cy plus d. F of x is cx plus d. I'm writing parentheses because there's this overall minus sign in front of it. Now let's do simplifications. You see that the d's will go away. You have a plus d minus d. And then you're left with terms that contain a c, so we can factor that c. Well, now the y minus x goes away. The function fully simplified down is just equal to a constant c. The limit of a constant is that constant. So the derivative of this function is just c, as we had said before. Last item, x to the n, where n is integer, larger than or equal to 2. So it could be like x squared, x cubed. And they're telling us for this item, you may find the following identity useful. difference of n powers can always be factored in this way. So a to the n minus b to the n. This is a useful identity to remember. It's equal to a minus b times a crazy sum containing, if you think about this, n terms where they are all summed together and they are all powers of a times powers of b. The powers of a are decreasing. You see n minus 1, n minus 2, n minus 3, all the way to a to the 0, which is 1. And the powers of b are increasing. So it's kind of abstract. This is, you can think of this as a difficult problem because of the abstract nonsense here, but the idea is very, very simple. So the function is x to the n. What is the derivative function? I'm going to use the y limit, the y form. F of y minus f of x over y minus x. All right, so this is y to the n minus x to the n divided by y minus x. So just looking at it, you might not know how to simplify this down because of the n. If n is 2, you actually would know what to do. Think about y squared minus x squared. If you write that as y plus x times y minus x, then you have your simplification. This time we just have a general n. The idea is exactly the same, of factoring this in such a way that y minus x is one of the factors. So this is the simplification that we need. The identity given to us in the problem was like this. All the way up to y to the 0 times x to the n minus 1 over y minus x. So it looks kind of messy, but after the y minus x is canceled, you are left with a polynomial of y's and x's, which does not give you any trouble when you're plugging in y equals x. The only question that you have to answer now is, what do you get when you plug in y equals x? What are we going to get from here? Well, from the first term, it will just be x to the n minus 1. From the second term, you have 1 power of x, and you have n minus 2 powers of y, but y is going to be x now. So in total, you still have n minus 1 powers of x in that term. And in fact, this is true for all of these terms here. Look at the next one, y to the n plus, n minus 3 times x to the 2. If y is x, those are 2 powers of x that get combined to x to the n minus 1. And remember that I told you there are n terms in this sum. But now they are all the same, so you can basically write n times that term. And that's the derivative of x to the n. Once again, which you'll probably remember if you've taken calculus before. This is called the power rule. So why did I do this in here? I just want to mention now, remark. We almost never compute derivatives this way, directly from the limit. What we just did. The exception is, I guess, piecewise functions, or functions that have formulas involving absolute value, which is also, you can think of that as a piecewise function, right? Anytime when you have a function that's not just one algebraic formula with powers and trig functions and exponentials, logarithms, then we usually have to do this definition. But in most cases, we're going to have practical rules that we are going to study later. So the thing that we just discovered, that the derivative of x to the n is equal to nx to the n minus 1, for example, that's called the power rule. Anywhere where you see an x to the n now, you will be able to differentiate it like that, 4 times x cubed. But we're going to talk about these rules later, not today. And I have another remark down here about the notation for derivatives. It's kind of a messy subject in notation. There are many ways to denote the derivative. There are other symbols. In particular, I want to mention a few ones here. So if you have a function with a name f, Instead of f prime, you can also write this symbol here, df over dx. It stands for f prime. So this symbol here is the name of the derivative function, whereas if you want to evaluate the derivative at a point, like f prime of a, then you would write it like this, df dx at a. Now, related to this, a common name for a function is y instead of f. You have functions which are given like this, y equals x squared plus sine x. This is a common way to denote a function. So instead of df dx, you would be writing dy dx. Okay, you just have to remember this is not a fraction. It's not like it's two numbers, dy over dx, and they're being divided like that. No, it's a symbol. Now, if you have a formula that represents the function, but you never gave it a name, like the problem says, consider the function x squared plus 2x, but without a name, and you want to find its derivative, then you can use this type of notation here, ddx of that expression. Or also like this expression prime. That's the same thing as ddx of that expression. But notice there is no y here now, or f. We don't have the name of the function, so you don't have that. ddx means derivative. Finally, the x can change depending on what you call the variable. If you have a function where the variable is not x, but t or whatever, then you change that accordingly. So for example, the derivative, here's a true fact. The derivative of x squared, f of x equals x squared, is f prime of x equals 2x. Now, all of the following are equivalent ways to say the same thing. If y is x squared, then dy dx is 2x. If y is t squared, then dy dt is 2t. If f of x is the x squared function, then df dx at the number a is equal to 2a. ddx of x squared is equal to 2x. ddz of z squared is equal to 2z. You should just get used to this. There are occasions when a notation is preferred over the other. As long as you're able to understand what they all mean, we shouldn't worry too much about this. Just be aware that the notations exist. There's even more if you are from a physics background. Derivative with respect to time is usually denoted by dot instead of prime. So you may see this also. But anyway, let's move on. Okay, so we've discussed how to compute derivatives. We need to talk about their meaning. What do they actually mean? We're going to give you two interpretations for what does a derivative mean. So here's the first one. This particular expression, the difference quotient of a function, what it represents is actually the average rate of change of the function in the particular interval between y and a. In fact, you don't necessarily need to have a larger than y, so it could be also between a and y. Just think about what it means. You're looking at the difference in the f values of those numbers and then divided by those numbers. If the numbers y and a represent time, for example, then you're looking at how much the function has changed over that interval of time. So it's an average rate of change. That's the difference quotient. But if you take y very close to a, which is exactly what you do in this limit process, then this average that you're taking right here is being taken over a very short interval around that number a, or close to that number a. So in the limit, it becomes an instantaneous rate of change. That's the meaning of the derivative, instantaneous rate of change at the point where you're finding the derivative. And just a remark here, if f represents position, there is a name in physics for the instantaneous rate of change of position. It's called velocity. So just like this example will show you. I have a quick example here. So you have a cannon located on the moon, and it's shooting an astronaut stuntman into the air. I have a formula given the height, f of t is the height in meters above the ground, as a function of time. t is time in seconds. So this formula has actually accurate numbers, given that we are on the moon. This is the acceleration of gravity on the moon, 8/5. So for example, the first question is asking you, what is the average velocity between t equals 0 and t equals 5? The way to answer this is exactly by this difference quotient. You're going to be looking at how much the height has changed over that interval and divided by how much time has passed. 5 and 0. All right, so if you compute, I wrote down the numbers in here. I don't want to waste time doing computations, but f of 5 will turn out to be 1500, f of 0 is 40, and this will give you 292. Physical units here would be meters per second. That's the average velocity of this stuntman between t equals 0 and t equals 5. Item B is now trying to take us to this idea of instantaneous velocity. Look at what they're saying. Use a calculator to find the average velocity between t equals 0 and now other numbers which are not 5, but rather 1, 0.1, 0.001. We're taking numbers which are smaller and smaller, closer to the number 0, and finding the average velocity over those smaller and smaller intervals. What do you expect is going to happen here? You should probably expect that the average velocity is increasing, because the closer you are to the initial moment where the cannon is shooting you, then the faster you are. Because, well, as time passes, you're going up, but you're getting slower with time if you are this astronaut. So for example, the average velocity between, let's write this, average velocity between time 0 and this time t1 that you're calling, which is just 1, is, this is how you compute average velocity, difference in positions divided by difference in time. So you have to compute this expression now according to that formula. You're going to find out at 298.4 meters per second. And I'm just going to give you the answers for the other ones. Between 0 and 0.1, it will actually be 299.84. And the next one, a little bit larger, 299.9984. Sorry, no extra 9. Anyway, as we expected, these are increasing, but not only increasing, they seem to be approaching a very specific number, which is going to be the answer to item C. Look at C. Can you guess what the instantaneous velocity was at t equals 0? The velocity at which he was shot from the cannon. The idea of this problem is to show us that the numbers that we found, because we were taking intervals closer and closer to 0, we can expect that the numbers are getting closer and closer to whatever the instantaneous velocity should be at 0. And we can see they're approaching the number 300 in this case. So hopefully this shines a light on the idea of instantaneous velocity and how it's computed by looking at a difference quotient, but then taking the numbers, let's call them y and x in this case. So you're taking the y closer and closer to x, which is exactly what you do with the derivative. That's why the derivative is the instantaneous rate of change. So now for the next problem, it still refers to that same function, minus 8/5 t squared plus 300t plus 40. Let me double check. Yes. We want to now actually using derivatives. We're not going to use this process of calculating closer and closer numbers. We're just using derivatives. find the actual instantaneous velocity at the times t1 equals 0 and t2 equals 375 over 4. So you just need to remember the instantaneous velocity at a time is the same thing as the derivative of the position function at that time. Let me actually write this down. Instantaneous velocity or rate of change at a time equals a is f prime of a. And we want to find it at the numbers 0 and 375 over 4. So I'm going to just indicate what you need to do in this problem. I'll give you the answer, but we have done very similar things just today. What is f prime of 0? You have to compute the limit defining the derivative. This is the limit. So you need to look at this function f and try to simplify this down, this particular limit with the function that's written right here. I don't want to do this because we've done very similar calculations earlier. So I will just go ahead and give you the answer, but we already knew this one. This is the one that we guessed from the previous exercise. The instantaneous velocity at 0 was 300 meters per second. Just try to find that value from this limit here. And the other one will be a 0. It's a similar thing. You need to be taking y to this number now, 375 over 4. The answer will be 0 this time. What happens is this turns out to be the instant in time where this astronaut reaches the peak of the trajectory after being shot from the cannon. You know, he's going to reach a maximum height, getting slower and slower until he reaches that height with velocity 0 before he starts falling again. Turns out to be this number if I didn't make any mistakes in my calculations. So that was the first meaning for the derivative as an instantaneous rate of change. Now, if you want to be more geometric about it, there is a second meaning, second interpretation. Let's talk about that now. This finally connects back to the ideas of the tangent lines. So once again, before thinking about the derivative, let's think just about this difference quotient. What does it represent geometrically? Well, if you have a function, let's imagine a small graph of a function like this, and you have 2 points, y and a. The points on the graph have a height of f of a, f of y. What does this expression here represent, the difference quotient? Basically, think about the line that connects those 2 points, which is a secant line. This expression is the difference in y values. I should probably not call them y because I have a variable being called y already. So difference in height, let's say, divided by difference in x values, horizontal distance, right? F of y minus f of a is the height of this triangle right here. And y minus a is the base of this triangle. You're dividing one by the other. What does that give you? Slope of this line. Slope of the secant line connecting these 2 points right here, a f of a, y f of y right here. That's what the difference quotient represents. Now what's going to happen if you take y closer and closer to a? Imagine this y point here moving closer to a. The secant line is also changing. What kind of line do you think it approaches as it changes? Imagine this point getting closer and closer to a until it approaches the tangent line. Can you imagine the black line getting closer and closer to the blue line in this drawing? So what does that mean? It means after you take this limit of the slope of the secant line, it should be getting closer to the slope of the tangent line. This is what the derivative means geometrically. f prime of a is the slope of the tangent line to the graph of f at the point a, or af of a. So here's an example. Consider the function 1 over x squared. See the graph below. This is the graph of 1 over x squared. Find the slope of the tangent line to its graph at the following points: 1 over 10, 100, and minus 100. Well, just looking at these points on the graph, let's try to draw the tangent line so we understand what they're doing, by the way. You can see that at 1 over 10 and at 100, these lines have a negative slope. They're pointing down, but it's much sharper at 1 over 10, whereas at 100, it's almost horizontal. So we're going to be finding negative values for these first two items. However, the first value will be very negative, a negative value with a large size. Meanwhile, the slope at minus 100 seems to be positive. This is a good enough drawing. Positive, but also not too big. So that guides our answers. But this is all actually not needed in this problem. They're just saying find the slope. We actually want the numeric answer. In other words, slope of the tangent line, that's the same thing as f prime of a. So it's the same type of problem from before. We want to find the derivative at these points. The function is 1 over x squared. So now, again, in interest of time, if f of x is 1 over x squared, we're going to need to find f prime of a for different values of a. So let's try to find it first. For example, using the h, well, the y definition is probably better here. Y goes to a. This is how you would compute this derivative. The function is 1 over a y squared minus 1 over a squared over y minus a. So as I was saying, in the interest of time, I will not do this calculation. It's a limit calculation. We should all be comfortable with this by now. I will tell you what the answer will be. It will be minus 2 over a cubed. How do I know that? I know derivative rules, which we're going to learn soon. I know how to differentiate a function like this according to the power rule. That's how I can guess this limit, but you should try. Now that I have found this derivative, we can answer the items right away. F prime of 1 over 10 is just minus 2 over 1 over 10 cubed. So the 10 cubed is 1,000. Because it's in the denominator of the denominator, it becomes a numerator. So this is minus 2,000, as we guessed from before. A negative number, which is very large. F prime of 100, item B, minus 2 over 100 cubed. Now that's, well, it is a negative number, as we had guessed. What is 100 cubed? Just a number with 6 zeros. It's a million. Again, as we guessed, negative, but with a small size. And f prime of minus 100 will be positive this time, because, well, minus 100 cubed is negative, and then with another negative in front becomes positive. Those are the answers to this problem. So again, it just asked us for slope of the tangent line, but that's a disguised way of asking what is f prime of a. Very quickly, if this is a theorem, I will not even mention the proof here. I mean, proofs are not really a part of our class. We don't need to know this. But it is a true fact that if a function is differentiable at a point, meaning the derivative exists and is a number, then it must also be continuous at that point. It is quite interesting if you're interested in math, in the abstract ideas, to go through a proof. It has nothing to do with our class, But basically, you assume that it is differentiable. So you assume that the limit defining the derivative exists. And you must conclude just from that fact, conclude that continuity is true. The three conditions defining continuity must be true. So it's a thing that is possible to do. But for us, why is this important? Well, think about it this way. If you have a function that is not continuous at a point, then it cannot be differentiable at that point. Because if it were, it would be continuous. So what is important for us is really this remark down here. A function cannot be differentiable at points where it is discontinuous because of the theorem above. And also there are other locations where it cannot be differentiable. We know this because of this geometric interpretation of the derivative. For example, as I mentioned before in the beginning of today's class, if the graph has a cusp at a specific point, then it's not differentiable because there is no tangent line. Look at the graph down here. At the number 1, we have a cusp. There is no definition of the tangent line. So you cannot talk about the slope of the tangent line, which is the derivative. And finally, places where the tangent line is vertical. This can happen. A lot of functions have this. Look at this function at the number 9. It does not actually fail the vertical line test. If you think about it, it is a function. This blue vertical line here is intersecting the graph in just one point. So it is a function. But at that location, the tangent line is vertical. And there is no slope of a vertical line. It would be either plus or minus infinity. So there is no derivative at the number 9. All right, so this is what we need to remember about differentiability. The three types of problems you can have: locations where the function is not differentiable, discontinuities, cusps, and places where the tangent line is vertical. So in this particular function here, f prime of -3 and 1 and 9 simply do not exist. So the function is not differentiable. Let me just see. This should be, yes, this one should probably be the last example for today's class, and then we'll be done. I'm giving you a function which is e to the minus x. Which of the following numbers is larger, f prime of 5 or f prime of -5? Now, if you knew how to differentiate the exponential function, which we will learn soon, then you could just calculate these numbers and see which one is larger. But we don't know how to differentiate. We have to be clever about how to find out which one is larger. And the answer is to look at the graph. We know what the derivative means in terms of the graph. You just need to remember what the graph of e to the minus x looks like. Well, e to the x, this one we should all know. It would have been this one, the graph that's just increasing all the way from 0 towards plus infinity. Because it's e to the minus x, though, what happens when you take a function and multiply its variable by -1, you're going to be flipping the function around the y-axis. So this is e to the minus x. That's the actual graph. All right, now the numbers 5 and -5. Remember that the derivative is the slope of the tangent line. Here are the tangent lines at those points. Both of them have a negative slope. We can see that from the shape of the graph. It's just going down. But which one is larger? Larger meaning, how do they compare? Is like this or like this? Well, the answer is f prime of 5 is larger. Like, for example, f prime of 5, looking at the graph, if you had to guess, both are negative, but f prime of 5 is a negative number with a small size, maybe like -0.1. And f prime of -5 right here, again, a negative number, but with a large size. Maybe that one is -10. I'm just guessing here. Those are not the answers, but to show us how I know which one is larger. All right. So this is just to reinforce this idea of the derivative as the slope of the tangent line. I will leave problems like this one for the recitation. We should be finishing this now. Let me see what was covered. Yeah, that's good. So we just needed to know how to compute a derivative. This is the most important definition. And then we have the two interpretations for the derivative as instantaneous rate of change and as slope of the tangent line. So this is what we needed to know for today's class.